Okay, so our speaker today is Ulrich Bauer, who will be telling us about persistence in functional topology.
Thanks for the introduction and thanks for the invitation. It's a great pleasure to be talking in this seminar after having presented already in the side seminar on Vittori's Rips complex. And today I'm going to talk about something that's less, in a sense, less geometric, but also there's geometry showing up. But it's about an aspect of persistent homology that dates far back in the history, and basically about an incarnation of persistent homology that's, as far as I know, the oldest in history, and it is in Morse theory, but in Morse theory in a more general sense than what you probably know. But it's kind of coming from the theory, like the motivations that Morse drove Morse to develop this theory. And these are variational problems. And here in the title, in the subtitle, there's one variational problem is showing up, Plateau's minimal surface problem. And actually, Morse developed a far-reaching generalization of the theory that we now know as Morse theory. And persistence plays an important role. I want to introduce first some ideas, like I'm going to show something pointing to the connections between persistence and Morse theory that some of you might have seen already. And then we'll go backwards in time and explore more things and generalize. So here's one example from my PhD thesis, so this is a bit older. This is a terrain. I think it's Mount Puget near Seattle. I'm sorry if I mispronounced the name. Maybe anyone who knows how to pronounce this can correct me. In any case, so what you should see here, regardless of how I mispronounce mountains, you should see that there's kind of a few prominent peaks, and it's easier to recognize like how many peaks, how many actual maxima of this elevation function you have if you also draw the contour lines. Here only the contour lines for maybe every 100 meters, and then you see there's actually quite a few. There's many kind of small and not very prominent little peaks. And what you actually see, or if you ask some mountaineers where are the mountains, they would say like this is a mountain, but that's not a mountain. And what you can actually do using Morse theory, there's a method that has been developed and has been put to use in the 60s when people studied the generalizations of the Poincare conjecture. Like, can you show there's this famous cobordism theorem. Basically, the goal is that if you have a sphere, you start with a Morse function, you want to cancel as many critical points as possible to eventually end up only with a minimum and a maximum. And this can actually also be put to use here. So this is a slight alteration of the function. But what I'm doing is I'm eliminating most of the critical points and leaving only the most prominent ones. And the prominence of these critical points is quantified by the persistence. And so what this here is, this modified terrain is actually a solution to this problem. You start with a function, the original function, and then you specify a tolerance delta. And the second function that I'm shown was a function that minimizes the number of critical points subject to this colorless constraint. In fact, this simplification problem here, I suppose, has many solutions. There's not a unique solution. And if you go back, I could also, in this large space of solutions, I could search for a function whose derivative looks very similar to the derivative of the original function, which makes these two terrains similar in appearance. So there's kind of a secondary aspect that is not part of the problem formulation, but this is why this function here looks so similar to the original one. So this is one instance of how Morse theory and persistent homology can be combined. And well, here's a slide kind of summarizing the different aspects of these two theories, Morse theory make statements about critical points and how they relate to the topology of the manifold, but also the topology of sublevel sets of the functions, so parts of the manifold. And as we have seen, there's a method. Originally, this was described on the level of vector fields, gradient fields, and what we've seen before was kind of the lifting of this method for functions. There's a way to cancel pairs of critical points. And the condition, if you want to eliminate two critical points, the condition to make this work is that there exists a unique gradient flow line connecting the 2 points. They have to be of consecutive index, let's say index I and I plus 1. And this is something like you see here. This would be maybe a saddle, and this would be a maximum, so index 1, index 2. And there's a unique gradient flow line here. And what that means in the smooth setting, and even also true in the discrete version developed by Robin Foreman, and much, much easier in this setting, you can kind of modify the gradient vector field and also the function, as we have seen, near this flow line, so as to eliminate this pair of critical points. And as you see, this picture is from these lectures on the H-cobordism theorem. So this is one of the several ingredients of the proof of this theorem. So this is kind of one of the two most important aspects of Morse theory. In persistent homology, you look also at sublevel sets of a function, but maybe from a slightly different angle. You relate homology of different sublevel sets. And while you also do this in classical Morse theory, you relate a sublevel set maybe to a slightly smaller one. In persistent homology, you take a more global viewpoint and you say like any two sublevel sets, and you're interested in how is the homology of these sublevel sets related. And this is what persistent homology asks for. So in a sense, the statements are more global in nature. Persistent homology identifies pairs of critical points. So like in Morse theory, we need to start with a pair of critical points, and if it's kind of admissible for cancellation, then we can modify. And persistent homology tells me, like, here's a pair of critical points. One gives rise to new homology, and the other one kills that homology again. So there's kind of an obvious like idea. Can we use the pairs that persistence identifies to carry out the cancellation? And well, another aspect of persistent homology is like if we have these pairs of critical points, birth and death, then the difference in function value is it's a quantity that's now associated to every critical point. That's kind of also an aspect that's not prominent in classical Morse theory. Okay. Yeah, so as I said, like if you put these two next to each other, then a very natural idea is to use these persistence pairs and try to cancel those using the methods of Morse theory. And this is actually what I've been doing in the previous example. Before we go there, I want to just mention this stability theorem, which plays a role. This is a classical result in persistent homology. If I have two functions, their distance in the supremum norm is delta, and I want to have some regularity assumptions. So, for example, it could be smooth Morse functions in a compact domain. And then we consider the sublevel sets, we consider their persistent homology, and we consider the barcodes of the persistent homology. Then they match up in a nice way that the endpoints are close to each other. So this is called a delta matching. If I have two matched up intervals, the endpoints are within distance delta, and there might be some unmatched intervals, but they're kind of matched to an empty interval, and so they have to have length at most 2 delta. And like what this tells us for this simplification problem, if I start with a function f and I look at a function g and I want to get rid of as many critical points as possible, and one important aspect is like every endpoint in these intervals corresponds to a critical point. So critical points can either start an interval or they can end an interval. They give birth or death to some homology class. And so, right, if I have an interval that has length more than 2 delta in F, then I can get rid of it in G. This is what the stability tells me. So this is a corollary of the stability. the critical points of F that have persistence 2 delta or more, let's say they have, those that have persistence strictly more than 2 delta, the number of those critical points is a lower bound on the possible number of critical points that any function G nearby can have. So stability kind of tells us which critical points I just can't get rid of. And of course, the natural question is, can I achieve this lower bound? And for surfaces, it's actually true. So what we have seen, I can cancel all the low persistence critical points, and I have to cancel them one after another in a certain order. So kind of the small ones before the larger ones. In particular, if I have a bar of this length, of some length, and then another one which completely encloses the first bar, I have to cancel the pair with a smaller bar first, and then in this order you can actually carry out cancellation of persistence pairs and get rid of all these small intervals. Okay, so that's basically the theorem behind the picture that we have seen before. And this is kind of one instance of how persistence and Morse theory are related that you might know from the TDA world. But there's much there's a much more fundamental connection in a sense, showing up in a kind of first incarnation of Morse theory. So here, just as a reminder, the definition of a Morse function, we have a smooth function on a compact manifold, and critical points are called non-degenerate if the Hessian is non-degenerate at the critical point. And then we can talk about an index, which is the number, the multiplicity of negative eigenvalues in the Hessian. And if we only have non-degenerate critical points, then we talk about a Morse function. This is kind of the classical definition. And just as classical is this theorem. I think this was the first statement about Morse functions. And it's kind of weird because it's a funny sequence of inequalities with alternating signs. And it's maybe not quite clear what these inequalities mean. We'll get to this in a moment because from the perspective of persistence, they have a very clear meaning. But well, they relate the number of critical points of a given index of a Morse function to the topology of the manifold. And this is kind of a local to global transition, right? Because the indices of the critical points are really just something very local about the function. And then this kind of enforces something about the topology of the entire space. But yeah, why else are these inequalities interesting? For example, there is a corollary. If you just look at the second inequality that you see here, and we can kind of rearrange this inequality and get something that's often called mountain pass lemma. So if we have a connected domain, meaning that 0 is 1, and let's assume that we have a function that has 2 minima or more. So this number of index 0 critical points is 2 or more, then, well, the second Morse inequality tells us that there also has to be a critical point of index 1, a saddle. And so, right, this just follows from rearranging this inequality here, putting M0 to the other side, and then inserting what we know about Betty 0 equals 1. And well, and M0 also was assumed to be greater or equal to 2. So we just insert these two assumptions, and we learn that we have at least one index 1 critical point. So this is actually like these kind of questions were important, like in a more general setting, like not in this nice setting of smooth functions on compact manifolds, but it was actually quite subtle, and we'll get to this later, to make statements about the existence of critical points of kind of higher index. In this setting is kind of a very nice corollary. So let me explain, like on this slide, you don't see much persistence, or maybe it's not obvious. Maybe some of you know that this is persistence, but let me just first make a drawing of an example. And then I'll say something more about why these Morse inequalities actually say something about persistent homology, and that's actually a good way to interpret them. Okay, I want to draw a torus, okay, with 2 bumps. So I get some interesting height function. And okay, then let me show the critical points of this function. There's a bunch of them. And I will also indicate their index. So this is a local minimum, index 0, another local minimum here. And here's index 1. Here's another index 1 critical point. Please ask questions, by the way, if something is unclear. Here's another one. So there's a whole bunch of index 1 critical points. And then 2 maxima, which are index 2. And I want to draw the persistence barcode for the sublevel set filtration, telling me when sublevel sets change their homology. So at this point, at this level here, a connected component of sublevels appears. And this will exist forever, right? There will always be one connected component. Here's another one showing up. And this is very short-lived. So it will, this second connected component corresponding to, can you see the mouse here? This will merge with this index 1 critical point. So yeah, you see every critical point ends or starts some interval here in this barcode. Yeah, that's it with H1, H0. Now let's move to H1. First homology, we have there's another critical point here that actually generates a new, it generates a new one-dimensional homology class. And this will also, this will remain, this will never be killed. And another one that also will not be killed. So these are essential classes. And then there's a fourth index 1 critical point that actually creates another one-dimensional feature, but again, this is going to be killed shortly after. And then finally, the last critical point, also of index 2, will generate the fundamental class of the manifold, so the H2 class. Okay. Okay, so now that we see the spark code, I can also say what is the connection to persistent homology. The Morse numbers, right? The number of critical points of a given index. Like we know each critical point in index I either generates an I-dimensional homology class, and then it is counted as number of births, and let's call the number of births of intervals in degree I, alpha I. And alpha I is the number of left endpoints of intervals in the ith barcode. And then, but an index I critical point can also kill an I-1 dimensional class, and let's call the number of those omega I-1. Okay, so this is one equality I have, and I also know the Betty number in degree I is number of births in degree I minus number of deaths. Sorry, minus omega I. So if I subtract these two, mi minus beta I get a sum of two death numbers. It's the number of deaths in degree I plus the number of deaths in degree I-1. Okay, and then I just if I take the alternating sum, which is what appears in the Morse inequalities, and I do this up to degree D. So -1 to the D minus I is my sign, and I take this difference that I just looked at, mi minus beta I. Then all these terms cancel apart for the largest one, so the number of deaths in degree I remain, right? And now, if you think about the Morse inequalities, simply state the now obvious fact that the number of deaths is non-negative, right? So what does this mean, right? if you know already, if you understand that there is a persistence barcode, then you already know the Morse inequalities. But now you see what they mean, right? They simply say, they state the quite obvious fact that the number of deaths can be negative. So that's kind of from that perspective, and that's really what all of these inequalities say. If you look at this calculation, so in that sense, the idea of persistence is already shadowed in these inequalities, and it should be pointed out that these inequalities, as far as I understand, are kind of the first instance, like the first glimpse at a larger picture that appeared in Morse's paper from 25. And of course, it's put maybe in a way that's like, there's more direct ways of understanding the picture. And I think like seeing the persistence barcode is kind of a clearer viewpoint than having these inequalities. But after the fact, this is what they mean. They have a very clear interpretation.
Uli, just to clarify, so D here is just any integer. It's not like
right. So we had these Morse inequalities for all degrees D, right? And for each degree D, you have one inequality of this kind. So which just says, number of deaths must be non-negative. Okay, so this is but maybe, well, nevertheless, remember that this mountain pass lemma is actually telling you something. If you rearrange it in this way, that might be of interest. So it's not just that you learn about this obvious fact, but you relating these two quantities, the number of critical points and the Betti numbers, is basically what you gain from these inequalities. Okay, as I said, so this is smooth Morse functions, kind of a very very nice setup. We want to generalize because also Morse's initial motivation was to look at a much broader viewpoint. Let me just go through this slide very quickly. This is what we just seen, the number of critical points. Like this is just the calculation that I did already again. Okay. Okay, so the generalization is what Morse called functional topology, and it's really Morse theory for variational problems. So instead of looking at functions on a compact manifold of finite dimension, we're looking at functionals which are not necessarily smooth, not even continuous. They're typically only lower semi-continuous, and the domains are some kind of high dimension, infinite dimensional function spaces. Banach spaces typically, right? So and it's interesting that like if you look at the first incarnation of persistence, it's not in this famous paper. I mean, this is the one that made most popular, but we know that around the same time, Vanessa Robbins came up with very similar ideas, and this was overlapping. But even 10 years before that, there was a whole lot of persistence ideas already in Patrizio Francini's work, and also Sergei Baranikov developed this kind of decomposition result for filtered chain complexes. That's really a statement about the persistence of filtration. So many incarnations of these ideas appear in the literature. And well, it's kind of difficult to say when this showed up first, but this is a paper here by Morse, like from appeared in the Annals in 1940. So this has been developed already in the 30s. And it has not received a lot of attention, but really very clearly ideas of persistence show up in this paper. And you see that one, like this is a screenshot I took several years ago, and it was only cited 9 times. But it was cited here in these papers about minimal surfaces, and that's really where the motivation comes from. And it's interesting because these minimal surface aspects were really a hot topic at the time. And the ideas of what we now call persistence were really crucial in solving a important, prominent problem at the time, that there was really a race among several analysts to be the first person like to solve this problem. But nevertheless, somehow this paper here that develops the theory kind of went mostly unnoticed. So let me explain what the motivation is. So this is Plato's problem. Given a closed Jordan curve, we want to find a surface of least area spanned by this curve. And I guess Plato's problem was whether this actually, for any Jordan curve, whether there even exists such a surface. This was difficult to prove, that given any curve, maybe put in some regularity assumptions to make your life easier, but does there even exist a minimizer of the area for bounding this curve? And let me just illustrate why, what are the subtleties with this question. Like we have seen, like in this example, you see a kind of symmetric curve, and so it has, like in A you see a curve that's not that's not a disk, right? This is basically a genus 1 surface here. But B and C are disk type surfaces, and that's what what Plato's problem in the simplest form is looking for, minimal surfaces of disk type. And you see B and C, if the curve is symmetric, they're also of the same area. So we have kind of two minimizers that are geometrically the same, just kind of they're related by a symmetry, right? Now, what you can do with this idea, like if you take more than one of these boundary curves and you join them by 2 tiny arcs, then you can already have now you can have kind of several minimizers with a very similar area. And if you continue this game, you can construct a rectifiable curve, like a curve with finite length that has kind of accumulation points, like uncountably many minimizers, and that just shows that it is difficult to, like with just these assumptions, it's difficult to control the space of solutions. And so the situation is more difficult than in smooth finite dimensional Morse theory. You don't have these nice isolated critical points. There's nothing that tells you that critical points would be isolated, and so this shows that if you want to study variational problems like this, you need to work with fewer assumptions on your function. But here, this is the theorem by Douglas that was one of the solutions to Plato's problem, and this I'm just mentioning this because this describes the functional that we are interested in, and it doesn't even describe the functional. And the good thing is we can basically work with many things as a black box. But nevertheless, and if Douglas's idea was that I can actually describe the minimal surfaces just by in terms of certain parameterizations of the boundary curve. There's a small condition here that 3 points on this S1 should be fixed, just to mod out conformal symmetries, right? So if you kind of have a conformal transformation, it would describe the same surface. But in a sense, like once you mod out the symmetry, then a given boundary parameterization has a unique harmonic extension to the interior. And then the critical points, you can set up a functional such that the critical points of this functional always precisely correspond to the minimal surfaces, meaning the critical points also of the Dirichlet energy of the two-dimensional thing. So the point here is not somebody that he moved the problem from just like a surface problem really to a problem only on one dimension low, or only on the boundary. Okay, but in any case, so for us, the only thing that we will take from this slide is that we have a functional, and we want to study the critical points because the critical points correspond to the objects of interest. They correspond to these minimal surfaces. And what's important is this is not going to be a continuous, it's only lower semi-continuous. Like most functionals in functional analysis, like as soon as you're finite dimensional, these functionals will no longer be continuous. Okay, and now we get to the problem that's similar to what we mentioned before. We're asking about critical points of higher index. So assume that we have a curve, as we have seen before, and this bounds two different stable minimal surfaces, really minimal surfaces that are really of minimum type, right? Local minima of the functional. the question that was open to show is that then there also exists a more complicated minimal surface that you would never see in nature because it's unstable, because it's not of local minimum type, but it's a higher index critical point. So this would be a index 1 here. And yeah, I mean, the challenge is to prove the seemingly obvious fact that such a thing exists. And you see that Morse and Tompkins and also Schiffman succeeded in pretty much at the same time with very different methods in proving this. And I want to talk about the approach by Morse and Tompkins because it's really a persistence approach, and I want to translate as much as possible of these ideas into the modern language and also use some of the persistence machinery that has been developed in the meantime to make this much more conceptual. And there's a reason like why I want to do this, because as I mentioned, somehow the work by Morse has been pretty much forgotten. And here is like, there's very few people who have closely read these papers, but one of them is Michael Struve. He's an expert in calculus with variation. And this is what he writes about Morse and Tompkins approach. Like, the technical complexity and the use of a sophisticated machinery tend to make Morse and Tompkins' original paper unreadable and inaccessible for the non-specialist. And that's kind of the judgment of one of the very few people who are really familiar with these ideas. And this book is nice because he lays out a lot of the ideas of Morse and Tompkins' approach, but he doesn't really go into the kind of persistence aspects. And that is what we tried here in joint work with Max Schmahl and Medina-Mardones. We try to explain like how persistence theory helps in clarifying this picture. And it's kind of analogous to the sketch that we have seen for the compact manifolds. Yeah, so this is why I guess this is why you see just this small number of citations. But one thing, like, this is how I found out even about this work by Morse. I read this survey by Raoul Bott, who was a student of Morse, and he also said something like this is, yeah, he mentioned some interesting things. Like, first of all, that the ideas that Morse developed, they were before Leray introduced spectral sequences, but they reflect a bunch of spectral sequences. And you're probably familiar with the connection between persistent homology and spectral sequences. There's a very nice paper on this connection by Saugata Basu and Lakshmi Pravida, for example. And what they describe there is actually also showing up in several older textbooks on homological algebra, where you see this connection between the spectral sequence of filtration and the persistent homology of the filtration. And also Bott says like that these papers are not easy reading, constitute another tour de force, but he wants to illustrate the idea. That was good. Like, if he hadn't done that, then I would not ever seen a connection. But he draws this example here of a curve with a height function, and then he says like there's a pairing between these two critical points. And we know from persistence, like, this is exactly one example that you would draw if you introduce persistent homology. And so this points to the fact that Morse with a different technical machinery basically also, like, he says that here is he calls these caps, and lambda is a non-linkable cap, and beta is a linkable cap, and these together form a pair in some sense, and they have a cap span, which is what we now call persistence. So you can look in this paper, but the approach is a bit more involved and more technical than the approach that we usually use, partly because of the level of generality that Morse is aiming at. But he has two ways of looking at this phenomena of persistence. One is very close to our sublevel set persistence approach, and the other one, using relative homology, is very closely connected to the spectral sequence viewpoint, or the spectral sequence of the filtration. So these both are there in this paper, and that's as I said before, any of these other concepts were introduced. Okay, but yeah, here's also an interesting quote from that paper. Like, Morse was battling the algebraic topology as a solitary figure he wanted to see topology from the side of analysis, and maybe that's kind of why his way of talking about these ideas, like if you read the paper, it doesn't feel like the language that we are used to when we think about algebraic topology. So so we try to extract the ideas, because there were really some ideas that are familiar to us, but there's also some because of the level of generality that he's aiming at, there's really something interesting to be learned from his ideas. And one aspect that we found particularly interesting is related to this idea of Qtane persistence modules that shows up in persistence theory. So Qtane means I have a persistence modules, I have a functor of a diagram of vector spaces indexed over the real numbers, seen as a poset. And Qtane means whenever I have two different real numbers, then the structure maps between them should be finite rank. Right? I don't care about the dimension of the vector spaces. This is basically invisible information to me, but the ranks should be finite. This is what's kind of observable. I mean, I'm already using a word that has been introduced in the persistence literature. We'll see this in a moment. One important example of Qtane persistence modules is given by Vitor's Rips persistence homology, because if you start with a compact metric space, the persistent homology of a compact metric space is not necessarily pointwise finite dimensional. So there might be infinite dimensional vector spaces showing up. There's an example by Dross showing that this might happen, but it's straightforward actually to show that the persistent homology is always Qtane. And the simple reason is that you can approximate any compact metric space by a finite one, and their persistent homologies will be interleaved, and that pretty much immediately tells you that they have to be Qtane. So that's a kind of very nice conceptual reason. So this is kind of one reason why Qtane, the class of Qtane persistence modules is kind of what's within reach of our methods and an interesting class. And also in the minimal surface problem that Morse and Tompkins considered. This is relevant because they basically wanted to establish sufficient conditions for a functional to have Qtane persistent sublevel set homology. And the reason why they want to do this is then you can actually still talk about persistence. And that's interesting. So they want to show that the minimal surface functional satisfies these conditions. And you can talk about persistence even though a Qtane persistence module might not have barcode decomposition, but it still has a meaningful persistence diagram. And that's due to an insight by Chazal, Crowley-Bovy, and De Silva. If you have a Qtane persistence module, you can construct a radical of that module. And there's a very nice and simple explicit description of this radical. At each index t, you simply take the image of all previous strictly previous indices. It's a submodule, and it's really this is also a radical in the module theoretic sense. And it is kind of, if you want to think of this in terms of barcodes, if there is a left endpoint, you're throwing away that left endpoint, and everything else stays where it is. So this turns out to always admit a barcode decomposition. And well, it is basically indistinguishable from the original module. This canonical inclusion of the radical into M has a co-kernel, and that this co-kernel is ephemeral, meaning that it's only vector spaces but all the maps between the vector spaces are zero. So in terms of barcode, this means only points as intervals. So completely irrelevant from the persistence perspective. So this is there's also a categorical way of basically making these vanish. And so in particular, the interleaving distance also between the radical and the module is zero. So we, from the perspective of interleaving, we consider them to be equal. And you can also phrase it in this way. So each Qtane persistence module has a unique persistence diagram. This is why it makes sense to talk about persistence diagram. And this is a description of like a complete invariant of the isomorphism type in what's called the observable category, which is really obtained from the full category by factoring out these ephemeral persistence modules. So persistence diagram here, in contrast to barcode, really just describes intervals in the barcode modulo the endpoints. I don't care whether the endpoints are there or not. And yeah, as I said, like here, the observable category is this category obtained as a quotient by modding out this category of persistence modules, which turns out to be a localizing subcategory. If you have seen these constructions by Gabriel and Serre, I think they describe in a homological algebra version of producing a quotient of an abelian category. And really what you're doing is you're treating all the ephemeral persistence modules as zero, and then you have this this kind of category with the same objects, but you're localizing certain morphisms. Okay, and that's kind of this is kind of one viewpoint which helps making the study of these problems more conceptual. In a sense, one thing you can do, like if you know that you have Butane persistent homology, and this is basically, I'm trying to rephrase what Morse has been doing in this language. So assuming that you have a Butane persistent homology and your function is also bounded. And by the way, my functionals typically are not bounded, but I can simply I can artificially create the situation, for example, by reparameterizing. So this is not really a restriction. But then I can observe that now the persistence diagram of such a function only has a finitely many bars above a certain minimum length epsilon. So and that's what makes it possible to state Morse inequalities in this setting, even though I might have an infinite number of critical points, but I don't have an infinite number of critical points that have persistence more than epsilon. And this is kind of necessary to even state a reasonable Morse inequalities, right? I first need to make sure that the numbers that should show up in these inequalities are all finite. Otherwise, yeah, what is the meaning of this alternating sum if there's infinities there? But this is kind of one idea that Morse had. If you focus on the large things only, and then things become finite, and that's really why he was interested in what we now call Butaneness, because this is kind of making these numbers finite, and it works for any epsilon, right? And this is also like, this idea basically can then be put to use to show the existence of an unstable minimal surface. As we have seen before, the Morse inequalities give you this kind of mountain class lemma in the finite setting, and here you can kind of restrict to some epsilon and also create the finiteness. So this is roughly how this idea comes about. Okay, so here's a statement, like again paraphrased from what Morse said. If you have a function f on a metric space, not assumed to be continuous, right? This really should apply to these functionals. It should be bounded below, which the functionals typically are. And another important condition, the sublevel sets are all compact. And then there's another condition here, which I don't want to define, locally connected. That's kind of a version of local connectivity, which you know from for spaces, and this is kind of a version for filtrations. And then Morse's theorem says that this is a sufficient condition for the function to have sublevel sets with Butane persistent homology. And he's using Vietoris homology, which is equivalent to Čech homology, by the way, to make this statement work. Unfortunately, like I'm not even defining this weakly locally connected, because there's a problem with this definition that makes the entire theorem incorrect. And the good news is it's fixable, but we need to change this, like what he defined, into something else. So instead of even going into the details of what goes wrong, he's just sketched like a very familiar space that is the counterexample. And I'm just saying what it is. It is the Hawaiian earring. and the function is 0 on this origin, and it's constant 1 everywhere else on the Hawaiian earring. And very clearly, the sublevel set persistence of this function is not Q-tape, because like if you go from level 1 to level 2, you have the same space, you have the entire Hawaiian earring, and it certainly doesn't have finite dimensional homology, so also the image doesn't have finite rank. But it satisfies, well, it's something you can verify if you look into our paper. It actually satisfies Morse's condition here. And so this is a kind of classical counterexample showing that this statement, as stated, can be correct. So let me just, instead of showing what's wrong, here's the correct version that we also generalize. We're only modifying several things. Morse's condition was homotopical, but since we only want to aim at Q-tameness, which is statement in homology, we also adapt the assumptions here to talk about homology and also only about finite rank instead of something being actually 0. So then the statement is, the assumption I want to make is, if I have a point in my space, and then I have two values that are larger than the function value of that point, and I take a neighborhood of the point in the sublevel set. Let me just try to sketch something here. So here's my point X, and here's a neighborhood of it in the sublevel set. And it can have many holes, infinitely many holes, right? But then there should be another smaller neighborhood in this smaller sublevel set. Let's say at level S, right? Here is level S, here was level T. And well, again, this neighborhood can also have infinitely many holes, but they're just the rank, like there should not be infinitely many holes in the smaller neighborhood that persist in the larger one, right? So there should be this neighborhood U. This one here is U, and the other one was V. And at least like these can be these can be both cheese with many holes, but somehow they should be only finitely many common holes between these neighborhoods. So it's really in a sense, it's a filtration adapted version of local connectivity seen from the homological viewpoint. And I really only want this to be finite rank. It could also require it to be 0, but finite rank is less strict. Okay, is this definition clear? So right, I have to be able to shrink the neighborhood within a smaller sublevel set and get the homology under control this way. And with this, now we can actually make a statement that gives a sufficient condition for Q-tameness. If the sublevel set filtration is compact and homologically locally small, as we've seen before, then it has Q-tame persistent homology, and hence we know it admits a persistence diagram. And what's important here is we don't require the function to be continuous. Like we said, functionals are not necessarily continuous. And in particular, the minimal surface functional still satisfies these assumptions here. And so we learn that the persistent homology basically of the minimal surface problem is Q-tame. And this can be used to fix the flaw in their proof, basically, that arises from this definition. What's interesting, it also applies not just to Vittor's and Čech homology as Morse imposed, but also to singular homology. This is again from Morse and Tompkins paper. I want to point at this place here. I want to point out two things. Like first, he says like these statements here that he shows are false if Vittor's cycles are replaced by singular cycles. So what he proves really only works for Vittor's or Čech homology, but not for singular homology. That's one thing I want to point out. The other one is there's a theorem here and a corollary. This is in a paper in the Annals. This theorem does not have a proof. And if anyone can tell me where would be the proof of this theorem, I would be very happy. But apparently, he was kind of citing another paper that's yet to be submitted also to the Annals. And I think that's the rank and span paper that I mentioned, but I don't know where the proof of this theorem is. And also this corollary is not an immediate corollary. So if our task is to explain other people, to non-experts, what Morse has been doing, we have to kind of redo some of the proofs here. So I'm gonna sketch very quickly also how you can actually connect homology and what we learned from this Q-tame persistence modules, connect back to critical points and critical sets actually in minimal surfaces. But maybe first some statement about here this Czech versus singular. The reason why Morse prefers to work with V-torus homology. But very clearly, if you have a compact sublevel set filtration, this is continuous from above in the sense that the T sublevel set is the intersection of all larger sublevel sets, U sublevel sets for U greater than T. So it's kind of a limit of a diagram. Czech homology actually, if you work with compact Hausdorff spaces, commutes with limits, right? So the homology, the limits are preserved by Czech homology, and so I can plug this in, and then the Czech homology of a sublevel set. Well, this is this limit, and then I can swap homology and homology functor and the limit functor, and I learn that the persistent homology is kind of at each index T is a limit of the larger indices. So in terms of this has a very clear meaning in terms of barcodes. This means that the barcodes are of this form left closed, right open, as we all know, like in the TDA constructions. So this is kind of I'm saying Czech cohomology here because as I said before, Czech homology does not necessarily have a direct sum decomposition. But in Czech cohomology, the arrows go backwards, and so the Czech cohomology is actually its own radical, and hence actually has a direct sum decomposition. So this is kind of a small detail here, but in a sense, you have the same intervals, and they have a meaning in both cases. And that's why you don't, like if you work with Czech homology, you don't have to pass to the observable category, because the persistence barcodes that you have already are kind of nice and under control. And these statements here that I'm making here about Czech homology are not true for singular instead of Czech. So that's why, right? And yeah, last slide, like how do you connect these algebraic considerations to homotopical ones? Well, I'm basically running through the sketch of the proof, but only by showing the lemmas that enter the proof. So if you have a persistence bar with endpoint T, then you can show that there actually has to be something that both Morse and Struve define a homotopically critical set. This is talking about critical sets instead of critical points, because you can have these plateaus as well, right? So larger critical regions that are local minima, for example. So that's one connection. You can go from, if you see a bar, then it has to be a critical set. The other direction does not necessarily hold, but you can have a critical set that does not change homology. And if you have a minimum type critical set, so you have a critical set and then you have kind of neighborhood where things only have a larger function value, then such a critical set actually is a topological summon of the entire sublevel set. So it's kind of closed and open in the sublevel set. And what this means in terms of homology, it only creates birth, right? So everything, the entire homology of this critical set is starting new homology in the barcode. So minimum type critical sets only birth, no death. And as a corollary, if you see a right endpoint at death, then it has to come from a non-minimum critical set, right? Critical set of non-minimum type. And well, that's what we basically do then. If there are two distinct critical sets and they are of minimum type, but the domain of the function is contractible, and that's the case for the minimal surface functional, then there's a critical set of non-minimum type. And basically that's how you see, like that's the idea, that's the outline of the proof, how you see the existence of a minimal surface that's not of minimum type. Okay, so that's it. We've seen like persistence diagrams can explain topology of functionals. They have an application in functional analysis as well. And Q-tameness ensures the existence of persistence diagrams, and local homological smallness ensures Q-tameness. So this is why we're interested in this property. And this basically gives a much clearer and more conceptual approach to Morse's ideas topology in the calculus of variations, Morse theory in the calculus of variations. And I'm pretty sure this is much more like conceptual and accessible to non-specialists now with a language that has been developed in persistence theory. So there's a chance that it will actually be useful to a broader audience also outside of TDA now. And that's all I want to say about this. Thanks for your attention.
Thanks a lot. Let's all unmute ourselves so that we can thank Uli for the very nice talk. Okay, do we have any questions? Okay, I might start with one myself then. Tell me if you'd find that the answer to the question is not interesting, you also don't have to talk about it. But I was curious, for this incorrect theorem that Morse published, is there some clear reason why he thought that his proof would be correct? Like, in which trap did he fall, or how could it have happened?
It's difficult to pinpoint, because I mean his proof is also like, we try to like work through the proof, but the proof was also not really clear to us. So it's difficult to say exactly where he makes a false assumption. But I think if you look at his notion, he calls it F connectedness, right? F is the name of the function, and his notion like appears in several papers, and with different definitions that are actually like not just differently phrased, but he had an earlier definition that we believe should still work. It's still a bit different from what we have here, but it might work. And then at some point he changed the definition and he relaxed it a little bit. And I think that's what happened. Probably he had a definition in mind, and then he phrased it in a different way, thinking that it would be the same, but it was actually different. I mean, because if you look at the, let me just show back where the key problem with his definition was. Here we are assuming this should work for any values s less than t, larger than the function value, and he said only there has to exist, like for any t larger that there exists an s, and that's basically the main thing that went wrong. And it's easy to miss, right? And I think that's what happened. He had an earlier version where he had an assumption like this, and then he rephrased it.
Great, that's very,
I guess,
very good moral of the story, that you shouldn't change your definitions midway. Okay, Alkanan.
Yeah, this is hopefully maybe a quick question. So does this technique of proving something about the one-dimensional plateau problem from the topological, the mountain pass style argument, is there anything, does this apply to, instead of a surface bounding a curve, you could have a, manifold bounding a surface? Does the same kind of proof carry through?
Well, yeah, so Morse and Tompkins prove that this condition is satisfied by the minimal surface function, and that's kind of the work, that's the real work in their paper. And if you manage to prove something like this for other functionals, then you're done, right? Because then the argument carries through, but you still have to establish this property for the functional of your interest. Right? So and then that seems to be also not entirely trivial. I think that's also one of the reasons why I'm not sure how easy this will be in practice to prove.
Do you know what kind of techniques, this is maybe a very general question, what kind of techniques are used to establish a result like that?
No, I don't know. I haven't, to be honest, I haven't worked through this part carefully where they established this condition. So I can't tell you much about this, but at least I can tell you, you can look in this paper by Morse and Tompkins from 39, and you'll see one instance of the techniques, one technique that has worked. And of course, like I said, similar, well, but it's more direct proof of Q-tameness that you see in these geometric settings. Yeah, so I guess that's all I can say to this question. That they did it in this paper, but yeah, I haven't checked carefully how they did it.
Fair enough. Thank you.
The next question is by David.
Hi, thank you so much. My question is just a general question based on your definition, your fine definition for Morse theorem that's on the slide which is shown. I was thinking, if you do a space or an intuitive map, that there's a neighborhood view.
Sorry, I have a very hard time understanding you. Some of the sound is muffled.
I was asking if your definition, that's your definition on slide 20, if you're you, the state view,
David, really quick. David, could you put your question in the chat?
Yeah, that would be easier.
Yeah, so if you don't mind, put in the chat, we'll get to it.
There's some issue with the microphone.
Yeah, maybe while David types, does someone else have a question that we could ask in the meantime?
I'll ask a question, Willie. So a little bit about the history. I mean, Morse theory is so foundational and used in so many different things today. But as you're saying, some of these papers, aren't all that cited all that much. Were these some of the first applications of Morse theory, or was Morse theory sort of used for other things before this, or did it only become popular later after it was used for things like this first, and then used in more general context? Yeah.
I mean, I believe that at least the motivation for Morse was always from variational problems, and he was always talking about calculus of variations in the large, and so he was always, I think he was always like, let's start with a finite dimensional setting, but he was aiming for problems of this type, and I mean, not just minimal surfaces, but also like I think these applications on energy functional on the loop space are also famous, and I think that is even before then people realized that you can also do a lot with manifolds, right? Finite dimensional topology, and I think it's also nice to look at Morse's papers and contrast that to the writing of Milnor to appreciate like how much of the expository, the celebrated expository style of Milnor has added to Morse theory, right? Because Morse's paper, I mean, he was kind of the first to observe these connections, but it is always much more difficult to parse, because he's always aiming for a high level of generality, and it's very difficult, I think, to see from his first papers from the 20s also like the simple messages that Milnor very clearly conveyed. And I think it was really, I mean, there's a big contribution by Milnor also in his lecture notes to this theory.
Thanks.
Yeah, I think that's all I can say. Okay.
In the meantime, the question is your U an inclusion map or a space in V which is a neighborhood of X?
Right, so U is a neighborhood of X that's also a subset of V, right? This is what we have. So, right, U is another neighborhood, right? And it is contained in this smaller sublevel set. It's a neighborhood in this sublevel set, and it's also contained as a subset in the first neighborhood V. Yeah.
Does this answer your question?
So it's a space, like it's a subset of V basically. But V is a neighborhood, so V is the intersection of this T sublevel set with some open set, and U is again an intersection of this S sublevel set with some other open set, and on top of that you have this inclusion relation. And both of them are neighborhoods of X. Both have to contain X.
Thanks. David, does this answer your question? I see you're typing again. Okay, but I think maybe we have asked already a lot of questions, so we can maybe stop the recording here and then maybe we can still ask some more questions afterwards.